look a bit more in depth at Cauchy sequences today, and the first thing we need to look at before we prove some theorem is that any Cauchy sequence is bounded, and when we say bounded, that means it's got an upper and lower bound. And we're not going to prove this, but it makes sense intuitively. If all the terms are going to get arbitrarily close to each other, I mean, the sequence isn't going to go off to positive infinity or negative infinity, is it? So seems like it has some bound. Obviously that's by no means a formal proof, but just to get your head around it conceptually, that makes sense. Now we're going to prove something called the Cauchy Convergence Criterion. And I'm not going to state the theorem writing it down, I'll just tell you the theorem, and then what I'll write down is the proof. So the Cauchy Convergence Criterion states that if xn is a real sequence, it's convergent if and only if xn is a Cauchy sequence. So this is saying essentially convergence implies that we have a Cauchy sequence, and knowing that our sequence is Cauchy implies convergence. So the implication goes both ways. So to prove it, it makes sense that we have to first assume we have a convergent sequence and show this is Cauchy, right? Then we've proved convergence implies Cauchy, and then we just start from fresh and we assume we have a Cauchy sequence, and then we try and prove that that means we get convergence. And then we've proved our if and only if statement. So we first assume that, we'll call this part I, that we have a convergent series, sequence, sorry. So if xn is convergent, okay, so xn converges to some alpha. So then we have epsilon greater, for all epsilon greater than 0, there exists n and capital N such that n being greater than or equal to n implies xn minus alpha is less than epsilon over 2, say. And this is because epsilon we're just taking as any number greater than 0. Epsilon over 2 is greater than epsilon, so we're just taking epsilon over 2 as our epsilon. But this is the formal definition of convergence. So this is all assumptions, okay? So for m and n greater than equal to n, we can consider xn minus xm. And you can see this is starting to look like our Cauchy sequences. We know that for a Cauchy sequence, xn minus xm, once greater than some n, the terms become less than some epsilon 2. So we're trying to use our assumption to prove this. Well, because m and n are greater than n, we know we can consider xn minus alpha minus xm minus alpha, because this is just, the alphas cancel each other out, so this is just equal to this. But we know that this is less than or equal to xn minus alpha, okay, plus xm minus alpha by our triangle inequalities, and then, but each of these, because m and n are greater than n, by this result here, are less than epsilon over 2. So this is less than or equal to, well, just less than, sorry. Is less than epsilon over 2 plus epsilon over 2, and that's equal to epsilon. So that's part 1 complete. Okay, we've shown now that if we assume convergence, we get a Cauchy sequence. Part 2 now, we're going to assume we have a Cauchy sequence. Okay, so from our result at the top, having a Cauchy sequence implies we've got a bounded sequence. Okay, so now we're going to use a result we had in the last video about bounded sequence, which is Bolzano Weierstrass, and we're just going to write BW for that. So that implies there exists a convergent subsequence x n k, where k is equal 1, 2, 3, so on, right? And it's convergent, so we say x n k converges to some alpha. So now to prove that our sequence is convergent, we need to show that this subsequence, our sequence converges to the same limit alpha as this subsequence. Okay, and if it does, then that will show that all the subsequences converge to the same limit, and our sequence converges to that, and therefore our sequence is convergent. Okay, so we're gonna let epsilon be greater than 0. Okay, and then we want to choose n1 such that for all n m greater than or equal to n1, we have xn minus xm, is less than epsilon over 2. Okay, so this is our this comes from our assumption that we have a Cauchy sequence. Okay, so that's fine, that's perfectly valid. Okay, and then we want to choose n2 such that for all nk greater than n2, we have x nk minus alpha is less than epsilon over 2. I'll keep putting less than or equal to, just a matter of habit. Sorry about that, it's less than. So this is from our Bolzano Weierstrass, okay, because we know it's a bounded sequence, we know there's a convergent subsequence, so this is all that's saying. Okay, but we're looking to show its convergence, so we can't have this m1 and n2, so we need to consider some n, and the way we choose n is as the maximum of m1 and n2, so whichever is bigger out of these, we choose that, and then we fix nk, so this is the subscript of our subsequence, it's not very good, k, greater than n, okay, such that xnk is in the subsequence. So we're basically saying we're considering values of nk greater than n, alright, but making sure those nk do correspond to values in the subsequence, and then for n greater than n, we can consider xn minus alpha, because this is what, and if xn minus alpha is less than or equal to some epsilon, or is less than or equal to epsilon, then we've proved that xn converges to alpha. But we can only use the facts that we know from our assumptions. So here we consider xn is equal to xn minus xnk. So what we're doing here is plus xnk minus alpha. So we're taking our nk almost as an xm here. Alright, so again, like the trick we did before, these xnk's cancel each other out. This is less than or equal to xn minus xnk plus xnk minus alpha. Okay, so hopefully that is making sense. And as you can see from we've got xn minus xm when we're greater than n1 is less than or equal to, is less than epsilon over 2, and xnk minus alpha is less than epsilon over 2 when nk is greater than n2. But we remember we picked n as the max of n1 and n2, so both of these things are holding for n greater than n. And here we're taking our xm as xnk, and then here that's clearly our second result. So this, or less than or equal to this is less than epsilon over 2 plus epsilon over 2, and that is not less than, that is equal to epsilon. So there we go. So we proved both ways. You might want to do some sort of statement at the bottom, just justifying you're working out or whatever, but this is sufficient for a proof of the Cauchy Convergence Criterion. Hopefully you understood this. If you've got any questions, please just let me know down in the comments. If you did enjoy this video and you like seeing more proofs of the theorems rather than just going through them all the time, then please let me know as well. If you did enjoy this video, please like and subscribe, and I hope to see you in the next one.